Okay, now what we have here, this is the second part of our chapter on the respiratory system. And what we're looking at here in the back end of chapter 23 are some of the volumes that are typically used to assess the efficiency of the respiratory system. So what you can see with this small peak and valley trace here, it represents what we call tidal volume, which is essentially the amount of air that you can move in and out of the lungs with normal breathing. Here you see this big peak and down here this big valley, okay? The distance between here and here is what we would call your vital capacity. That's the maximum amount of air that you can physically move in and out of your lungs with total effort. It's composed of your expiratory reserve volume, your tidal volume, plus your inspiratory reserve volume. Generally, when we take these different volumes, the mechanisms you're going to use in lab are spirometers that are what we call blowout spirometers. And so we can directly measure tidal volume and expiratory reserve and vital capacity. We have to impute or compute inspiratory reserve volume again by using the equation that indicates that inspiratory reserve is simply the sum of the ERV, the IRV, and of course the TV. Okay. Some other volumes we need to be aware of include minute ventilation, which is the total air moved into and out of the respiratory system each minute, which is the tidal volume times the respiratory rate. The respiratory rate or frequency, which is the number of breaths you take in a single minute. The anatomical dead space, which is simply the air inside the respiratory system that serves to essentially keep the system open. Okay, it's not available really for gas exchange. It's formed by the nasal cavity, the pharynx, trachea, the bronchi, and the terminal bronchioles. And the anatomical dead space is not something that you could physically expel. We would have to actually remove your lungs and your upper respiratory from your body and roll them out with a rolling pin in order to get that dead space air out. But there are displacement techniques that we can use to measure it, like plethysmography. Physiological dead space is the anatomical dead space plus the volume of any alveoli in which gas exchange is less than normal. So, for instance, over time, what can happen is the lungs can become damaged due to exposure to particulates, tar, and whatnot, and that can result in death of alveoli, but also the accumulation of scar tissue, and that would contribute to physiological dead space because that's not gas exchange surface area. And then alveolar ventilation, which is the volume of air available for gas exchange in a single minute. Now, last time we were together, we were talking about some of these different laws that relate gas exchange. And one of the things I told you guys is that you can learn all these separate laws, memorize them, but honestly, I like to take the approach of using the perfect gas law as kind of a catch-all to deal with a lot of these problems that are concerned with gas exchange. And the perfect gas law, simply stated, is PV equals nRT, where P is pressure, V is volume, N is the number of moles of gas, R is the gas constant, and T is the temperature in degree Kelvin. So we can write that down here, PV equal nRT. Okay? And this really covers all these other laws. Law of partial pressure simply states that the total pressure of a given gas against the sides of the container is equal to the sum of the pressures of the component gases in their molar ratios. Water vapor pressure is going to be the pressure exerted by gaseous water in a mix of gases, and the air in the respiratory system is humid because of the mucus that lines it. Okay, so we have to take into account the water vapor pressure when we're looking at total pressure. Diffusion of gases through liquids obeys Henry's law, where the concentration of gas in a liquid is determined by its partial pressure and its solubility coefficient. One of the things we're going to learn is that carbon dioxide is much more soluble in water than oxygen is. Okay, Also, we have to keep in mind that solubility is related to temperature as well. So that's one of the things that we're going to take into account when we look at gas exchange. So let's take a listen to gas exchange during respiration.
Respiration serves as a means for the body to exchange gases with the atmosphere via the blood. The partial pressure of oxygen, PO2, in the air in the alveolar spaces in the lungs is greater than the PO2 in the blood, so oxygen diffuses into red blood cells from air in the lungs. Also, the partial pressure of carbon dioxide, PCO2, in the air in the lungs is less than the PCO2 in the blood. So carbon dioxide diffuses out from red blood cells and into the air in the lungs. Oxygen-rich blood is carried through pulmonary veins to the heart and then pumped through systemic arteries to the body. The PO2 in the blood is higher than the PO2 in the body tissues, so oxygen diffuses out from red blood cells at the body tissues. Also, the PCO2 in the blood is lower than the PCO2 in the body tissues, so carbon dioxide diffuses into red blood cells there. Oxygen-poor blood is carried through systemic veins back to the heart and is pumped through pulmonary arteries to the lungs, where gas exchange again replenishes the blood with oxygen and removes carbon dioxide.
Okay, so what are the physical principles that govern gas exchange? Well, diffusion of gases through the respiratory membrane depends on the thickness of the membrane. Obviously, the thicker, the less efficient the exchange is going to be. The diffusion coefficient of the gas, which is a measure of how easily it passes through a liquid or a tissue. Carbon dioxide is 20 times more diffusible than oxygen, and the surface area of the membrane, the partial pressure of the gases in the alveoli, and the blood all are going to play into this diffusion coefficient. Surface area, also very important. The more surface area you've got, the more diffusion you're going to have. This is why emphysema and cystic fibrosis and lung cancer reduce surface area and impede gas exchange. And then differences in partial pressure. Remember that gas is always going to move from an area of high to low pressure. Normally, partial pressures of oxygen are higher in the alveoli than in the blood, and the opposite is true for carbon dioxide, and that's going to govern simply the direction of movement. Okay, if you're ever in an area where you're inhaling air that's high in carbon dioxide, you'll never forget it because it'll produce a very adverse effect. If you want to mimic this effect, if you ever get a chance to get some dry ice and you put it in water, the vapor that comes off is CO2, and if you were to inhale a small amount of that vapor, you would have an extremely adverse reaction to it. And this is, again, a survival instinct to keep us away from areas where CO2 levels are high. That's why we have that adverse reaction. Now remember that carbon monoxide, which is a cousin of CO2, does not produce that same adverse reaction. It is odorless, colorless, and tasteless, and as a result, if we're in presence of carbon monoxide, we wouldn't know it unless we were near a CO detector. It's a metabolic poison. It chokes the electron transport chain, basically constipates the chain so that you can't produce ATP. It also it competes with oxygen for binding sites on hemoglobin. So carbon monoxide is basically bad news. Okay, if we look at the relationship between alveolar ventilation and pulmonary capillary perfusion, one of the things that we're going to understand is that the pulmonary system is always going to try and make certain that perfusion is maximized where ventilation is high, and ventilation is maximized where perfusion is high. And this is the opposite of the way it is in systemic tissues. And the reason is we want to make sure that we can get as much oxygen into the blood as possible. So this increased ventilation or increased pulmonary capillary blood flow increases the efficiency of loading oxygen into the blood and getting CO2 out. Shunted blood is that which is not completely oxygenated. There are physiological shunts where deoxygenated blood returning from the lungs comes from two sources. This is blood returning from the bronchioles and blood that comes from the capillaries surrounding the alveoli. The regional distribution of blood flow is determined primarily by gravity, but it can be determined in addition by the concentration of alveolar oxygen. Low oxygen levels causes the arterioles to constrict and to get the blood away from areas of the lungs that aren't well ventilated, whereas high oxygen levels cause the arterioles to dilate. Okay, so this is the reverse of what it is in the systemic tissues. Oxygen, note that it moves from the alveoli into the blood, which is almost completely saturated with oxygen when it leaves the capillaries in the lungs. The oxygen partial pressure in the blood decreases because of mixing with deoxygenated blood. As a result, oxygen moves from the tissue capillaries into the tissues when we're at the systemic end of the circuit. Carbon dioxide moves from the tissues into the tissue capillaries and moves from the pulmonary capillaries into the alveoli. And the reason for this, again, in systemic tissue is that CO2 production is rather high owing to the fact that metabolism is going on, and the end products of metabolism include carbon dioxide, water, and of course heat, and that also essentially leads us to conclude that the pH is going to be lower in metabolically active tissues than it would be in tissues that were not. And it turns out that higher temperatures and lower pHs, in addition to the carbon dioxide gradient, are perfect for hemoglobin releasing its oxygen and carbon dioxide being taken up both by the plasma and by the RBCs. So what we're looking at here is just the movement of oxygen and carbon dioxide in the body. Okay, so take a listen.
Fresh air entering the lungs carries oxygen to the alveoli. The amount of gas in air or of gas dissolved in a fluid can be expressed as partial pressure, which is measured in millimeters of mercury. The partial pressure of oxygen in the air within the alveoli is 104 millimeters of mercury. Carbon dioxide that enters the alveoli from the blood causes the carbon dioxide concentration in the air of the alveoli to be 40 millimeters of mercury. Carbon dioxide is continually removed from the alveoli as air is expired. Blood coming from the heart at the arterial ends of the pulmonary capillaries has a partial pressure of oxygen, or PO2, of 40 and a PCO2 of 45. Therefore, oxygen diffuses from the air in the alveoli into the blood, and carbon dioxide diffuses from the blood into the alveoli because of these differences in partial pressures. Oxygen and carbon dioxide diffuse until there is no difference in partial pressure in the air and the blood. At this point, there is no more net movement of O2 or CO2. Therefore, at the venous ends of the pulmonary capillaries, the PO2 in the blood and alveoli is 104, and the PCO2 in the blood and alveoli is 40. Some oxygen was removed from the blood to nourish lung tissue. Therefore, the PO2 in arterial blood leaving the heart is 95. Oxygen diffuses out of the arterial ends of tissue capillaries into the tissue fluid, then into the cells, and carbon dioxide diffuses out of the cells into the tissue fluid, then into the blood because of differences in partial pressures. At the venous ends of tissue capillaries, the PO2 in the blood is equal to the PO2 in the tissue fluid, and the PCO2 in the blood is equal to the PCO2 in the tissue fluid, resulting in no more net movement of O2 or CO2. The blood now carries the O2 and CO2 to the lungs. In the body, all of these exchanges occur simultaneously.
And this is going to talk a little bit about the changes in partial pressure of oxygen and carbon dioxide as we run between the pulmonary and the systemic circuits.
Fresh air entering the lung carries oxygen with a PO2 of 160. The presence of moisture in the lung results in reduction of the PO2 to 104. Fresh air entering the lung carries carbon dioxide with a pCO2 of 0.3. The carbon dioxide delivered to the lung from the blood raises the pCO2 to 40. At the arterial ends of the pulmonary capillaries, oxygen diffuses from the air in the alveoli into the blood, and carbon dioxide diffuses from the blood into the alveoli because of differences in partial pressures. As a result of diffusion, at the venous ends of the pulmonary capillaries, the PO2 in the blood is equal to the PO2 in the alveoli, and the pCO2 in the blood is equal to the pCO2 in the alveoli. With no differences in partial pressure, there is no more net movement of oxygen or carbon dioxide. Oxygen diffuses out of the arterial ends of tissue capillaries into the tissue fluid, then into the cells, and carbon dioxide diffuses out of the cells into the tissue fluid, then into the blood because of differences in partial pressures. At the venous ends of tissue capillaries, the PO2 in the blood is equal to the PO2 in the tissue fluid, and the pCO2 in the blood is equal to the pCO2 in the tissue fluid, resulting in no more net movement of oxygen or carbon dioxide. The blood now carries the oxygen and carbon dioxide to the lungs. In the body, all of these exchanges occur simultaneously.
Okay, hemoglobin is a protein that's perfectly designed to transport oxygen in the body. Oxygen is transported by hemoglobin at about 98% clip and at about a 1.5% clip in the plasma. So if we didn't have hemoglobin around, the blood would have a hard time transporting oxygen. Oxygen hemoglobin dissociation curve is going to describe the percentage of hemoglobin saturated with oxygen at any given partial pressure. The oxygen hemoglobin dissociation curve at rest shows that hemoglobin is almost completely saturated when the pressure of oxygen is 80 millimeters of mercury or higher. At lower partial pressures, the hemoglobin is going to release the oxygen. And so what you're looking at here is just the hemoglobin dissociation curve, and what we're tracking here is the oxygen saturation versus the partial pressure in millimeters of mercury. Okay, so the take-home message in this graph is that we can see that the hemoglobin is perfectly adapted to transport the oxygen between the pulmonary and systemic tissues due to its properties. Okay, here you can see the partial pressure in the tissues during exercise. You can see that the oxygen saturation of hemoglobin is going to be approximately, call it 25%. But why is that a good thing? Well, because in the tissues, what do we want to do? We want to unload as much oxygen as possible to get it to the tissues that are performing their work, right? Because the oxygen is necessary to make ATP. Partial pressure of oxygen in tissues at rest, close to 75%, okay? The metabolic demand is lower, thus the saturation of hemoglobin fits the metabolic demand for oxygen. And then in the lungs, okay, we get close to 100% saturation at around, I'd call it about 105 millimeters of mercury partial pressure. And this is ideal again for scavenging the oxygen from the air that you breathe and then getting it to the tissues as required. So here we see perfect adaptation of the protein for its function. Now the Bohr effect simply describes the effect of pH on oxygen hemoglobin dissociation. Essentially, bottom line, the more acidic the environment is, the more the hemoglobin is going to release its oxygen. The less acidic the pH, the more the hemoglobin is going to hold on to its oxygen. Now, the reason, again, that this is a perfect adaptation for hemoglobin to carry oxygen around the body is because in metabolically active tissue, we tend to have lower pH due to the production of carbon dioxide and organic acids. the result is that the hemoglobin is going to tend to release its bound oxygen. So this occurs because the decreased pH yields an increase in protons. These combine with the hemoglobin, causing it to change its shape and releasing more of its bound oxygen. Temperature, okay, higher the temperature, the more likely the hemoglobin is going to release its oxygen. And again, perfect adaptation of hemoglobin for metabolically active tissue. Metabolically active tissue is warm. Why? Because heat is a byproduct of metabolic activity. As a result, as temperature goes up, oxygen saturation in hemoglobin declines, and the result is that we're going to tend to release now the bound oxygen. In addition, okay, it turns out that an increase in carbon dioxide concentration results in a decrease in pH. Carbonic anhydrase causes carbon dioxide and water to form carbonic acid, which will ionize. This will result in a drop in the pH, and of course, this will result in a change in the conformation of the hemoglobin, causing it to release its oxygen. In addition to that, something we need to be aware of is the fact that at high carbon dioxide concentrations, there are allosteric sites on the hemoglobin to which it will bind, resulting in conformational changes that further promote the release of bound oxygen by the hemoglobin. Bisphosphoglycerate is released by red blood cells as they utilize glucose for energy. It binds to the hemoglobin and also induces the release of oxygen. Bisphosphoglycerate, again, you could think of kind of as an organic acid in a way, okay? And the effect is direct but also indirect, okay? There's a direct interaction of BPG and hemoglobin, and then there's also an indirect effect as a result of the effect on pH, okay? And so this is just a look at how the curve shifts, and the take-home message here is that if we look at the left-hand curve, you're seeing the shift to the right as hemoglobin saturation declines, with a drop in the pH, an increase in the CO2 concentration, and an increase in the temperature, okay? And that shift to the right indicates a lower affinity for the bound hemoglobin. And again, to demonstrate that, all we have to do is essentially draw a trace here. So let's use a red line, okay? And let's pick, oh, I don't know, an oxygen concentration of 30 millimeters of mercury. And then if we draw our line straight up, we're going to hit the blue curve here, okay, at about 58% saturation, okay? That's in the presence now of acid conditions, high CO2 content, and high temperature. If we continue upward, okay, the curve prior to the shift, physiological conditions that promote oxygen binding to hemoglobin, look at the saturation here, okay? The saturation close to 70%, whereas again in this other curve, saturation's close to 58 to 60%. Okay, so you can see as the curve shifts to the right, the amount of saturation is going to decline. Okay, so again, take-home message here, right? Drop in pH, increase in CO2 concentration, increase in temperature, all going to shift that curve to the right. Okay, the curve shifts to the left as these conditions reverse. Okay, so in the tissues, the conditions that are predominant are going to be the blue curve, and in the lungs, the conditions that are going to predominate are going to be the red curve shown here. Okay, the oxygen hemoglobin dissociation curve shifts left, the pH increases, the CO2 concentration drops, and the temperature drops a little. Okay, and the result is a higher affinity of hemoglobin for its bound oxygen. So this is a pretty sweet deal. This means that this pigment is designed perfectly for this task. Now, Before we're born, we have a problem, we have a challenge, which is that we have to steal oxygen from maternal blood. And we do this as a result of the expression of a gene called fetal hemoglobin, which picks up oxygen from maternal blood. It has a higher affinity for oxygen than either the alpha or beta chains of adult hemoglobin. The concentration of fetal hemoglobin is 50% greater than concentration of maternal hemoglobin. The oxygen hemoglobin dissociation curve in fetal hemoglobin is to the left of adult hemoglobin, so the fetal hemoglobin can steal the oxygen from the maternal hemoglobin, which is exactly what we want to happen at the level of the placenta. Bisphosphoglycerate has little effect on fetal hemoglobin and does not cause it to release oxygen. The movement of CO2 out of the fetal blood causes the fetal oxygen hemoglobin dissociation curve to shift to the left, meaning there's higher oxygen affinity. Simultaneously, movement of CO2 into the mother's blood causes the maternal oxygen hemoglobin curve to shift to the right as a result, again, of the Bohr effect, okay, which is that the action of the dropping of the pH on the affinity of adult hemoglobin for its oxygen. So bottom line, when you've got metabolically active conditions, high CO2, low pH, high temperature, the hemoglobin is going to unload. It's going to dump its oxygen, and it's going to some extent, actually directly bind to CO2, but mostly it's going to promote via diffusion the movement of CO2 out of the tissues and into the blood. Most of the CO2, as we see here, is transported in the plasma. CO2 is transported as bicarbonate in combination with blood proteins, 23%, but bicarbonate by far the majority at 70%, and directly in solution with plasma about 7%. So most of the hemoglobin is in this form as bicarbonate. Some of it attaches directly to the hemoglobin and causes that shift in shape that causes it to dump more of its oxygen. Okay, that's a condition of hemoglobin we call carbaminohemoglobin. Hemoglobin that is released oxygen binds more readily to CO2 than hemoglobin that has oxygen bound to it. Essentially, the way that you can look at this is called the Haldane effect. You could think of the hemoglobin and the carbon dioxide as fighting for binding to, rather the oxygen in the hemoglobin fighting for binding to the hemoglobin at sites that are not identical, okay, but that essentially complement each other in the sense that as CO2 binds to its allosteric sites, the oxygen binding sites become less accessible. By the same token, as oxygen binds to its sites on the heme, it tends to force the CO2 out of the globin. Okay, so it's sort of a push-me-pull-you effect with oxygen and CO2 on hemoglobin. In tissue capillaries, CO2 combines with water inside red cells to form the carbonic acid. This dissociates, making bicarbonate and hydrogen ions, and of course, we know what effect the hydrogen ions have on the affinity of hemoglobin for oxygen, causes it to drop. Tissue capillaries have high CO2. This enters the red blood cells and reacts with water, forming the bicarbonate and the protons. The chloride ions enter the red cell and the bicarbonate ions leave, and this we call a chloride shift to maintain charge on either side of the RBC. The hydrogen ions combine with the hemoglobin, and this lowers the concentration of bicarbonate, and hydrogen ions inside the red blood cell promote again the conversion of CO2 to bicarbonate. In the pulmonary capillaries, the CO2 leaves the red blood cells, and this results in formation of additional CO2 from carbonic acid. The bicarbonate ions are exchanged for chloride ions, and the hydrogen ions are released from the hemoglobin. Increased plasma CO2 concentration lowers the blood pH. The respiratory system then regulates this by regulating plasma CO2 levels. And so this diagram kind of shows you what's happening here at the level of the tissue cells. Okay, so we again see that the gradient is going to favor CO2 movement out of the tissues into the plasma. Most of it will stay in the plasma, but a fair percentage of it enters the RBC, is transformed into carbonic acid via carbonic anhydrase, and then the proton production that results from the ionization of this acid has a two-pronged effect. The bicarbonate will leave the cell via an antiporter while chloride is pumped in. At the same time, the protons will bind to the hemoglobin, reducing its affinity for oxygen, and then along with the concentration gradient, this enhances the unloading of the oxygen into the tissues. At the same time, carbon dioxide that isn't shunted down this pathway can bind directly to hemoglobin, forming carbaminohemoglobin and further decreasing the affinity of the hemoglobin for its bound oxygen. And this entire process reverses in the pulmonary tissues, because what happens now, as oxygen concentration in the alveoli is high and its concentration in the blood is low, oxygen diffuses across the respiratory membrane into the RBC. As it binds to the hemoglobin, has a two-pronged effect, forces the CO2 out, forces the bound protons out. The bound protons then associate with bicarbonate, and we're going to form carbonic acid. At the same time, carbonic acid will dissociate into water. The CO2 that is produced from the ionization, well, let's say from the dissociation, is then going to diffuse across the RBC into the plasma and out into the expired alveolar air, okay? At the same time as the oxygen competes for its heme binding sites. The allosteric CO2 binding sites are going to change their shape. CO2 is going to have a lower affinity for the hemoglobin. It'll be forced out of this tetrameric protein, and it too will diffuse down its gradient into the alveolar tissue, and then we'll blow it off, okay, as we exhale. CO2 levels in the exhaled air are higher, obviously, than in the inhaled air. How do we regulate ventilation? Well, you can probably kind of guess as to what sort of factors will increase or decrease regulation or ventilation rate, right? Higher temperatures are going to raise ventilation rate. Higher CO2 concentrations in the blood are going to raise ventilation rate. Acid blood will raise ventilation rate, okay? And all this is the result of chemosensors that are stationed throughout the circulatory system, and they check the blood chemistry. The medullary respiratory center has dorsal groups that stimulate the diaphragm, the main muscle of breathing, and ventral groups that stimulate the intercostals and abdominals. The pontine respiratory group is involved with switching between inspiration and expiration. But of course, again, the timing of all this is regulated, again, at the level of the brainstem. Okay? More important that the brainstem stay intact, because otherwise your vital signs would shut down. So let's take a look at rhythmic variation. The medullary respiratory center neurons are constantly active. It receives stimulation from receptors and stimulation from parts of the brain concerned with voluntary respiratory movement and emotion. The combined input from all sources causes action potentials to stimulate respiratory muscles. The result, increasing inspiration. As more and more neurons are activated, the muscle contracts more powerfully. Stopping inspiration, the neurons stimulating also are responsible for stopping. They receive input from the pontine group and stretch receptors in the lungs. The inhibitory neurons are activated, and the relaxation of the respiratory muscles results in the blowout. Expiration, remember, generally is a passive process, unless you're doing forced expiration, in which case the abdominal muscles are called into play. Now, apnea is simply the cessation of breathing. It can be conscious, and sometimes it can happen while we're asleep. Eventually, CO2 levels increase to the point that the respiratory center overrides the cessation of breathing most of the time. Okay, there are unusual situations in which this system breaks down. Okay, and this is what we call central sleep apnea. In newborns, we suspect that this may be a contributing factor to SIDS, sudden infant death syndrome. Okay, hyperventilation causes a decrease in blood carbon dioxide content, resulting in peripheral vasodilation. This causes a drop in blood pressure that can result in fainting. And again, to sort of counteract this, one of the things that we tell people is to breathe into a paper bag, rebreathe their own carbon dioxide, and get their blood pH back down to normal. The cerebral and the limbic system control respiration voluntarily via emotion. So you can, to some extent, modulate your breathing rhythm. But eventually what will happen if you, say, hold your breath for an extended period of time is you'll pass out, and then the brainstem will take over again. How does chemical control play into this? Well, we kind of already touched on this. CO2 is the major regulator, but indirectly through pH change. Again, an increase or decrease in pH will stimulate chemosensitive areas, causing a greater rate and depth of respiration. Obviously, you can sort of tease out how this would work. As the pH drops, the respiratory rate and the depth of breathing increase. As the pH goes up, the reverse happens. Okay. Oxygen levels in the blood affect the respiration when there's a 50% or greater decrease from normal levels. Conditions can also exist where you have abnormal amounts of CO2 in the blood. Hypercapnia describes too much CO2, hypocapnia, lower than normal CO2. And the bottom line in both of these conditions is the respiratory rate will adjust. In hypercapnia, respiratory rate and depth of breathing will increase. In hypocapnia, the reverse will be the case. And so what you're looking at here is just some of the impacts on respiration rate and depth of breathing. Higher brain centers obviously have an impact on the brainstem. There are medullary chemoreceptors that are responsive to CO2 levels and pH levels, which are in a way kind of the same thing due to the fact that CO2 in water produces carbonic acid, which in turn lowers the pH as it ionizes. And then carotid and aortic bodies also are chemosensors, okay, so they react to changes in pH, carbon dioxide, and oxygen levels in ways you would expect, right? As the pH levels drop or the CO2 levels go up or the oxygen levels drop, the rate and the depth of respiration will increase. Herring-Brewer reflex is essentially a braking system in the lungs so that they don't overinflate and pop. And there are proprioceptors in the muscles and the joints that also play a role in the rate and the depth of breathing, in addition to receptors for touch, temperature, and pain stimuli. Okay? So all this heads to the medulla and the pons, and then modify the rate and the depth of breathing. Chemoreceptors are specialized neurons that respond to changes in chemicals in solution. Okay, so you can think of these as, I don't know, little dipsticks, if you will, that are constantly checking on the chemical composition of body fluids. Central chemoreceptors are chemosensitive areas in the medulla that are connected to the respiratory center, and then there are peripheral chemoreceptors in the carotid and aortic bodies that are connected to the respiratory center by cranial nerves 9 and 10. How does pH govern this? Chemosensitive areas in the medulla oblongata and the carotid and aortic bodies respond to blood pH changes in, again, a predictable fashion, right? As the pH drops, the rate and the depth of breathing increase. As the pH rises, the rate and the depth of breathing decrease. Okay? So these areas respond indirectly through changes in CO2, and the carotid and aortic bodies respond directly to pH changes. Okay? So you're really looking at two ends of the same phenomenon here. Remember that rising CO2 begets a drop in pH in body fluids. Okay, how does CO2 play into this? Well, small changes in CO2 trigger a large increase in the rate and the depth of respiration. Remember that hypercapnia we already talked about is a greater than normal amount of CO2. Hypocapnia is the reverse situation. The chemosensitive area in the medulla is more important for the regulation of carbon dioxide levels in the blood and pH. Carotid bodies respond rapidly to changes in blood pH due to exercise. How does chemical control of ventilation play a role? Well, oxygen, surprisingly, isn't nearly the driver of respiration you would think it is. But the carotid and aortic bodies do respond to decreased oxygen content by increased stimulation of the respiratory center to keep it active despite drops in O2 levels. Hypoxia is just a condition in which the oxygen levels fall below normal value, and obviously to fix this we have to increase the rate and the depth of respiration to get the oxygen content back to normal levels. And so what you're looking at here is just, again, the same sort of scenario that we were looking at in previous chapters when we were dealing with shifts in blood chemistry brought about in other systems, okay, or changes in physiological conditions. This is just a homeostasis diagram. What we look at here, okay, as an example, we start with blood pH increasing, okay, so you can predict what the outcome of this will be. As blood pH increases, what's going to happen to the rate and depth of breathing? It's going to decline, okay, but how is this active? Well, medullary chemoreceptors are going to detect increases in blood pH caused by a drop in blood carbon dioxide, causing a decrease in the rate and depth of breathing. The result, we slow down the rate and depth of breathing, CO2 builds up in the tissues, the pH drops, and we're back where we need to be, okay? Flip side, if we begin here, blood pH begins to decrease. Too much CO2 in the blood, pH getting too low. Chemoreceptors in the medulla pick this up. The decrease in the blood pH caused by an increase in CO2 causes an increase in the rate and depth of breathing. We pick it up, and the result then is that the pH rises back to normal. The Herring-Brewer reflex is just, again, a braking system that limits the degree of inspiration and prevents overinflation of the lungs. In infants, this plays a role in regulating the rhythm of breathing and preventing lung overinflation. And in adults, the reflex is important when tidal volume is large, as in exercise. We don't want to overinflate the lungs because they could rupture, right? That would be bad news, because then we'd have air inside the thoracic cavity over and above physiological pressure, and the lungs would collapse. Ventilation will increase abruptly upon exercise. The movement of the limbs has a strong influence. A lot of this is a learned response. The ventilation begins to increase gradually. After an immediate increase, the gradual increase occurs about 4 to 6 minutes later. Then we hit anaerobic threshold, which is the highest level of exercise we can attain without causing a big change in the blood pH. If we exceed this, lactic acid buildup by the skeletal muscle will eventually result in basically exercising to the point of failure. Okay. Other modifications on ventilation include activation of touch, thermal, and pain receptors that affect the respiratory center, or sneezing or cough reflexes. Those are protective to get irritants out of the lungs, and an increase in body temperature that produces an increase in ventilation, again as a response to a change in metabolic rate. How do exercise regimens affect respiratory rate? Well, athletic training is going to increase vital capacity, and residual volume will decrease as well. And why is this? Because the muscles of breathing will become more powerful. Diaphragm will become more powerful. The intercostals, the abdominals, the sternocleidomastoid, the erector spinae, all of those will become more powerful, and the result is our vital capacity will increase. At maximal exercise, tidal volume and minute ventilation go up. Why? Because we need more oxygen to the tissues to support the activity. Gas exchange between the alveoli and the blood increase at maximal exercise, as does alveolar ventilation. Increased cardiovascular efficiency leads to greater blood flow through the lungs. Makes sense, right? You're going to breathe more rapidly. You're going to load more oxygen into the blood per unit time. To keep up with this, what's going to happen to the heart rate? It's going to beat more rapidly, and it's going to beat more with more power. And the whole point of that is to get the oxygen to the tissues that need it in order to support the activity. Unfortunately, we all get old. As we get old, a lot of components that affect our respiratory efficiency decline. vital capacity begins to drop due to the fibrotic condition of the lungs. Also, the fact that a lot of the joints in the rib cage begin to calcify result in a restrictive condition that don't allow us to inflate the lungs nearly the way it used to. Residual volume and dead space increase. A lot of this is due to, again, the accumulation of particulates and scar tissue all through the respiratory system, and the ability to remove mucus from the respiratory passageways decreases simply because that pseudostratified ciliated columnar epithelia becomes less effective at moving the mucus up towards the oral cavity, right? Gas exchange across the respiratory membrane is reduced. Why? Well, because there's less membrane there, and what membrane you've got is probably coated with particulates or scar tissue, and the result, again, is it's more difficult for you to load the oxygen into the bloodstream. Okay, that brings Chapter 23 to an end. I will see everybody in class, and have a good night.